what we would like to do now is to build upon and improve, really, this kind of a representation. There's one awkward thing about it, really, which is that after a while you start drawing so many arrows and worrying about where their bases are, the diagrams can start to become a little bit messy. So there's this new representation that I'd like to introduce, and this is something known then as the field, not a field map, but a field line representation. It's a little bit of a misnomer because actually, as we will see, they aren't usually lines. Most often they turn out to be curves, but that's the term that people use. And what the field line representation consists of then are directed, so these are, as you'll see, they have a particular direction to them, directed curves, really, they're not lines, directed curves which are always, they're always either parallel, they're always, I'm sorry, not either, they are always parallel, or mathematically we could say tangent, to the electric field, the field E. So let's try to show you what that representation would do for the particular situations that we've looked at so far. Now these turn out to be kind of special cases, and in fact, as we're about to see, we're going to end up with straight field lines, but that's not normally the case. But let's show you what that definition would mean in the present context. So in order to do that, let me here, maybe I'll change my pen color to something a little different. I'll pick a red pen color for you. So what I'm supposed to do then is I'm supposed to make a directed curve. So let me start at some point here. Maybe I'll start at my favorite point right here, right? Now I'm supposed to make a curve that's always parallel or tangent to the field. So I'm going to start at this point, I'm going to move along the field, and I have to stay always parallel to the field. But I'm lucky because as I move along this curve that I'm starting to define, the electric field, I'm always am parallel to it because the electric field is always directly outward. So this would be a field line, and I should extend this as far as I can. It's going to go outward towards infinity, and also notice it doesn't necessarily start at this point. I can extrapolate it backwards. It originates actually at the location of the charge. Finally, it's a directed curve. On the diagram, I would also include an arrow on that line, so I know that the direction of the flow, if you will, along that line is outward. So that's just one field line. I would complete the map by sketching a whole series of field lines. Again, here I can follow the curve and stay always tangent to it, which would make a line that's directly outward. Here I'd have an outward line, always directed outward, as you can see in this case. And the field line representation would be what I'm drawing for you here in red, would include those arrows so I know the sense of direction on each of these so-called curves, which actually are straight lines in this case. Now, for the case of the linear charge distribution, again, I'm directed completely inward, so the field lines now follow the same kind of a pattern. I might start out here, and I have to move parallel to the field, but as I move, I'm along a straight line, I'm maintaining a parallel relation to the field. So I have exactly kind of the same radial lines as I had before, but now, as you can see, these lines are directed straight inward. And now also that it's not so messy as I'm drawing many arrows like I would in a field map, I can also include in here, the field lines that are coming in at other angles. Oh, that was not straight. I'm going to fix that curved line. But here you get the idea of what these are supposed to look like, and they would include their arrows. Similarly, in the planar case, they would originate on the plane, right? And then they extrapolate upwards, staying nice and parallel to the electric field always, like so. The one little shift here is that, well, once I'm below the plate, the electric field down here actually points downward. So these lines go downward, straight down like so. And the switchover where the lines kind of switch direction is right when they make contact here with the surface of the plate, because the second you switch to below the plate, at that very instant, your line will be then directed downwards. So that's the basic definition. Now, in the cases that I've shown you so far, of course, I'm going to switch back my pen. The cases that I've shown you here so far, of course, they just turned out to be straight lines. Being straight lines, then it's easy to figure out what they should be. If I'm in a situation where the electric field direction, and we're going to look at this in an example in a moment, is starting to change as I move along my line, I'm going to get into a situation where there are some curves. And so for this, I'm going to need a more mathematical kind of a definition or statement. So if I want to state this more mathematically, what I'm saying is that if I think about the points that define any one of these particular field lines, there's a set of points, and I'm going to characterize that set of points along a given line by some kind of a parameter. So there will be these locations of along my given field line, which I will call x, and it's a collection of points described by a parameter that varies as I move along the line. A line is a one-dimensional object, so I'll have a single parameter, and for reasons that will become clear in a moment, I'm just going to call that t, although right now it doesn't necessarily have anything to do with time t. Now, if this is a curve, mathematically, you will recall, the way we calculate the tangent vector to the curve in vector calculus is by taking the derivative of the parameterization with respect to the given parameter. And this then defines the tangent to the curve, and I want this always parallel to the electric field, so I can set it proportional to the electric field vector, the electric field times any constant. I will just happen to choose a constant equal to 1. That will maintain a nice parallel relationship, which is all that I really need. And I have to be, of course, parallel to the electric field at the point where I am at any given instant. So this is the electric field measured at my location, vector x I'm calling it, at time t, or at parameter t. That would then become my mathematical definition. Now, the reason why I want to introduce this, and why I've been talking about time in particular, is not just to have an equation that we can solve, but we can make a very nice connection to the fluid analogy. You remember, in fluid world, I can set up a situation where the electric field actually is directly equal at every point in space, mathematically equal to a velocity field I will set up with a series of fluid sources. So if I think, again, using my electric world, water world analogy, so I'm over here in water world for a moment, and I imagine setting up one of my mechanical devices to be an analog to my electric field. What this equation would become then is that I'm looking at curves, right, whose tangent vector, whose derivative then equals, and recall that the electric field, its correspondence in water world is the velocity of the flow. So this would be the velocity at location x of t. And if we step back and look at this very carefully, now this should look familiar to us, right? What this is just a description that the rate of motion, right, the motion of the fluid at any point in space matches of this path along my trajectory, which is defining my parameterized path, which is defining my field line, is always exactly equal to what I would expect if I were just tracking the velocity of particles moving along with the fluid. So there's a concept in water world that goes along with this precise equation that just says I'm looking at the path followed, path x of t, by what's called a tracer particle. It's just a particle that moves along with the flow field of the fluid so that the time derivative of its position matches the flow of the fluid. So this is the path of a so-called tracer particle, which is otherwise known in fluid mechanics as a streamline, because it goes along with the stream of the flow. A streamline in the fluid. So the streamline in the fluid then corresponds back here in the electric world to what we would think of as a field line. What that means then is all I have to do is to picture my liquid analogy where I put in point sources wherever my point charges are, and then I can imagine the flow using my physical intuition about how fluids behave. I imagine that flow, and I throw in some tracer particles that will just move along with the flow of the fluid. They will trace out streamlines, and those streamlines then will tell me exactly what the field line should look like. And we can see in these simple examples that that's definitely going to work, right? If this electric field represented the flow field from having a point source here that's pumping fluid out, very clearly if I put any little tracer particle, I guess I better go back to red here for a moment for my tracer particle. If I go then for my tracer particle, he's going to come out of my little point source, and then he's going to be ejected, and he's just going to keep flowing directly outward. And by thinking of what these little tracer particles do as they come out in different directions from my charges, I'm able to exactly reproduce the field lines. Very good. So let's then try this out now in a specific example.